DM services. We provide product design services and manufacturing support. So I'm just here today in the middle of a DIY project outside. So that's my latest one. But today I'd like to talk about cycle times in particular with injection molding. So depending on who you ask, you'll get different cycle times quoted. By the way, if you like this video, would you mind subscribing and liking the video? So depending on who you ask, you're going to get different cycle times quoted for your plastic part. Typically the injection molder will want to run your mold slower, so less wear on the machine and perhaps less equipment malfunction or breakage, so it'd be safer to run it slower. However, that may not always be to your advantage as the customer. Also the unit price, so when you're calculating the unit price, an extended cycle means it takes longer to run your order and your unit price can go up then. Likewise with the tool maker, the tool maker will want to build a tool and doesn't want to be constrained by a cycle time, so the cooling efficiency of the tool may not be optimal, and tool makers will usually quote quite long cycle times as well. However, I've found typically you could have cycle times anything from like 5 seconds to 30-35 seconds on a typical injection mold. Obviously the faster you can produce your parts, the less time it's going to take to fulfill orders and the more parts you'll get out, so there's a saving in that for you. But so I've developed this just a simple Excel worksheet to explain and to help calculate what a cycle time on an injection mold should be. If you like this and if you find the worksheet useful, just drop me a line. I think the contact details will be below, and I can send it to you. So let's jump on the computer here and I'll go through this worksheet with you. Thank you. Okay, so here we are on this worksheet here. At the top here we just have a summary of all the different sections within a typical injection molding cycle, and here we have some of the detail. So I've just coloured out the areas that you don't need to put in any detail, just the white boxes that you need to insert figures. So we'll just go down through it and we'll have a look at it here. So injection fill time, put in 1.5. I just put a note here. Estimated injection time usually under a second. That'll be fairly typical. For larger parts, I'm going to say over 200 grams to use 2 seconds cycle time. So that's your injection time. Look, there's no hard and fast rule on that. You want to try and get the plastic into the mold as quick as possible, and it's typically okay, there is a science behind it, but you're trying to get the plastic in there as fast as you possibly can at a lowest pressure that you can, so there's a compromise there to be had. But yeah, typically under 1 second I would say to fill the cavity, not to pressurize it, hold it, just to fill the plastic into it. So you're looking at somewhere between under 1 second for small parts, and you're looking at larger parts go with under 2 seconds. So that's the fill time. Then the pack and hold time. Pack and hold time plus your cooling time. So if we use this table over here, we can see a list of materials down here, and we can see wall thicknesses here. So we have 1 millimeter, 2, 3, 4, 5 and 6 millimeters. Typically your wall thickness will be somewhere between 1 and 3 millimeters for most plastic parts. So let's say we take a polypropylene here, you're looking at approximately 9 seconds for 2 millimeter. Considerably goes up the cooling time to 22 seconds at 3 millimeters. So the actual wall thickness of your part has a huge effect on your cycle time, just to note that. But just as a reference here, let's say a 2 millimeter one, okay, you can have 10 seconds, or 3 millimeters, 22 seconds. Now I've added on a few seconds for larger runners perhaps. If we have a large runner, let's say it's a 10 mil runner, but I know it's going to be sufficiently solidified or hard cooled sufficiently, let's say 50% of it, the middle of it may not be cooled, but the outer core, outer surface of the runner would be. We're going to say 50% of that. So even like with a wall thickness, a typical runner being, let's say, 6 millimeters. I would be looking at probably taking a figure of half of that. So, 30-40 seconds. If I take cooling time for half of that runner. So that's the cooling and holding time there. You can work it off this table over here. So then we go on to the mold closing. This is all calculated and I sum it up for the cycle time. But the mold closing then, calculated from mold closing table down here. So what information we need to put in. So the mold opening distance, how far is the mold actually going to open? That will depend on the thickness of your part and so on. So let's say it needs to open 150, or that's what I've taken there. Now your thickness of your robot as well, if you're going to use a robot to pick off the parts, that would also be, you need to put that in there as well, because that has a add up to the total distance of your mold open distance. Okay, so then they ask the question, how fast do you want to run this? The mold closing speed, do you want it at slow, medium or fast? Down here I have different speeds for whether you choose slow, fast or medium. These would be fairly, okay, there's no exact science in this, but they would be fairly typical in the industry, that kind of speeds. Likewise with your robot, how do you want to run your robot? Can you run it fast, slow or medium? And these are typical cycle times for getting out of the mold, getting into the mold. So these kind of robot out times, that's where I've put that. That's come from there, depending on what speed you want to try and run that robot at. So a tin wall part that you need fast cycling, you need the robot working really hard to get in and out there quickly. With a thick, larger part, where you might be just picking a sprue, fast. You can get the robot in there quickly, but let's say a thicker part, a bigger part where you have maybe an operation to do in the tool, you would typically run the robot slower. Okay, so time to operate the hydraulic cores. If you have core sequence moving in and out in your tool, it may take some time to move these cores in and out, a few seconds. So you could typically put that in there. Secondly, the delay times for the sliders. If you can put in, if you have sliders in your mold and you need to delay the time on it, you can put in a time there. Okay, so we try to calculate then the total mold closing time based on the sum of these four parts here, and that will give us a mold close time, and that's the 2.5 seconds up there. Likewise with the mold opening, so we're just asking how fast you want to run this mold at when you're opening the tool. The time to operate hydraulic cores, if you have, delay time for sliders if that's in the tool, and then we're adding these times to the mold open times and the robot in times to give us a total mold open time. And yeah, we're adding that to the cycle time. And then finally your part ejection. So again, we're asking what the part height is, how thick the part is that needs to be pushed out of the mold, how fast we want to run the ejectors, and the number of ejector strokes that you need to push this part off, and if there's a delay time in it. So fairly self-explanatory, this Excel sheet, and it just adds up these cycle times then for your part. So I hope this is of some use or benefit to you. Like I say, if you want this worksheet, just contact me, details are below, and I'll send you this worksheet, no problem. Also, if you could like and subscribe to this channel, that'd be great too, that'd help me out. Thank you, all the best.